Welcome. We were discussing the motion of two particles that interact with one another through the gravitational interaction, and we started off with discussing the generalized two body problem, and we saw that the angular momentum is conserved. So, it has to be the generalized two body problem, we reduced it to a one body problem of the reduced mass and the motion of the center of mass. The center of mass moves like a free particle, so it is not of interest. So, we are now interested in the motion of the reduced mass around the center of mass, and this is the central force problem. The angular momentum we saw is conserved in such an interaction which is isotropic, it does not depend on the direction. So, we have the conservation of angular momentum, and we also have the conservation of the energy, because the interaction is not explicitly time dependent. So, we were using these two conserved quantities and the fact that the orbit will be in a plane to determine the orbit. So, we have the conservation of angular momentum. Let me write that down again. So, the angular momentum, or let me start with the energy, the conservation of energy E. We had calculated this was m by 2 r dot square plus L by 2 m r square, L square by 2 m r square minus alpha by r. So, let me remind you what each term stands for. This was the kinetic energy of the radial motion, this was the kinetic energy of the tangential motion, which we wrote in terms of the angular momentum. Please note that I have changed the symbol for the angular momentum. We had used capital M earlier, but then I realized that it could be confused with the total mass. So, I have replaced it with capital L. Capital L is the angular momentum. So, this is the kinetic energy of the radial of the tangential motion, and this is the essentially the this gives rise to the centrifugal force, this potential, minus alpha by r. This is the gravitational interaction. So, we have this, and we also have the angular momentum L, which is m r square d phi dt. And we are interested in calculating the motion, the orbit, the orbit of the reduced mass around the center of mass. So, this is the center of mass, that is the origin, and this is the particle reduced mass, which this distance represents the separation between the two particles that we were originally interested in. So, we are interested in the motion of this r as a function of phi, that is the orbit. So, we would like to calculate the orbit in the plane of the motion right now, and we proceed. I had outlined how we proceed in the last class. We proceed by eliminating time from this whole thing, and it is also convenient to introduce x, which is 1 by r. Okay. And using x, which is 1 by r, and using this, the time derivative. So, the time derivative of r can be written as L by m into the phi derivative of x. Okay, we did this algebra in the last class. So, this is straightforward algebra, nothing much to it. So, you have to just replace dr dt in terms of dx dt, and you can use this to replace derivatives in terms of t with derivatives in terms of phi. Okay, so, doing this you are led to the relation that dr dt, which occurs over here, can be written as the angular momentum by mass into dx d phi. Okay, this is straightforward algebra, and if we substitute this here, then we have the energy E the energy is equal to L square by 2 m dx d phi whole square plus L square by 2 m into x, where x is 1 by r, minus my x square, that is right, minus alpha into x. So, the energy, the conservation of energy can now be written in this way. And the same exercise can also be done if I had some other interaction instead of gravity. The only change would be that I would have, instead of alpha x, I would have the other interaction that were there. Okay. So, in case you are interested in some other interaction, you have to just replace this term minus alpha x with something else. Okay. So, this is the final expression for x in terms of phi. It's a you can see that it's a very solving this is quite straightforward. So, what we can do is we can take all the terms involving x onto one side, and there is only then going to be, so we can take E. Okay, let me just write down this equation in a convenient way. What we will do is we will multiply this whole thing, this whole equation, with 2 m by L square. Okay, we will multiply it with 2 m by L squared. So, I will get if I multiply it with 2 m by L square, and I can take these two terms on the left hand side, what I will get is dx d phi square is equal to E prime is E divided by E into 2 m by L square minus plus alpha x, alpha prime x, minus x square. So, all that I have done is I have multiplied with 2 m by L square and then taken this to the left hand side, taken this to the left hand side, and I get this, where E prime is 2 m E by L square, alpha prime is 2 m alpha by L square, right. And this can be integrated straight away, it is not difficult at all. And if you integrate this, what you get is phi minus phi prime is equal to the integral phi minus phi 0, where phi 0 is an arbitrary constant of integration. This is equal to dx divided by the square root of E prime plus alpha prime x minus x square. Right. So, we have obtained a formal solution. All that you have to do is to do this integral, and this can in principle be done for any kind of a potential interaction, but the integral cannot be analytically done in most cases. It can be done, luckily it can be done for the gravitational interaction. So, we will just do this integral for the gravitational interaction, which is what we have written down here. So, the way to proceed, this integral is not very difficult at all. The way to proceed is as follows. What we do is we write E prime we write this as E prime minus x minus alpha prime by 2 square. So, we want to write the term that occurs below the square inside the square root, and I am writing it as E prime minus this. So, I will have x square and I will have minus x square, which is there. I will have plus alpha prime into x. So, I have one extra term which is minus alpha prime square by 4. So, I have to add that plus alpha prime square by 4. Okay. So, this is the term that occurs in the under the square root in the denominator, and what we will do is we will so this is the term. What we will do is we will say that x minus alpha prime by 2 is equal to E prime plus alpha prime square by 4 to the power of half cos theta. So, with this substitution, this is quite straightforward now. The denominator, this term, you can see now it becomes, I can take this term, the square of this, so this term will become, if I call this A, this will become, this is A square and this is A square cos square theta. So, this will become A square sin square theta, right, and dx is minus A sin theta d theta. So, now we can go back to this integral phi minus phi naught is equal to, so dx will be minus A sin theta d theta, and this whole term in the denominator will become A sin theta. So, A sin theta will cancel out, and what we are left with is that phi minus phi naught is equal to minus theta. That is all. Right, the integration is done, and we can put back this now over here. So, if you put it back over here, what you get, we can, and this phi naught is an arbitrary constant. It essentially tells us what is the value of r when phi is equal to 0. It tells us where the origin is, origin of phi is. So, we will choose phi naught to be 0. With this choice, the equation, it becomes, what we have is so we have the solution is over here basically. The solution is that 1 by r is equal to alpha prime by 2 plus, I will write this as A plus A cos phi. Okay. So, we have obtained the solution to the problem that we want to solve. It is now, it is not in terms of the energy or the other integrals of motion, but we can do that. It is most convenient to write it in the following way. I will, let me write it in this. it is most convenient to write it in the following way: P by R. Let me put it on a different sheet of paper. So, it is most convenient to write it in this way: P by R is equal to 1 plus E cos phi. Okay. So, this is nothing, I have the same thing, I have just taken this factor over here and called it P, and I have taken A and divided it by alpha prime by 2 and I have called it E. And if you go back and work out what the value of P will be, you have to replace alpha prime and E prime, etc. The value of P is L square by m into alpha, and the value of E is 1 plus 2 L square E by m alpha square to the power of half. Okay. So, this is nothing but straightforward algebra, you have to just work back, and P we know is, we have seen is right. So, you can identify what P is from this expression and what E is from this expression, and write them in terms of E and L and alpha and the mass of the particle, the reduced mass, and you can arrive at these expressions. This is just straightforward algebra, I am not going through it. Okay. So, this is the orbit of the reduced mass under this central central force motion, which is gravity. Okay. So, let us now spend a little time interpreting what we have just worked out. The first thing is that this equation, it describes what is called a conic section, which I am sure all of us are familiar with. So, this equation that we have worked out, the equation between r and phi, it defines what is called a conic section. Okay. So, this is a conic section. And the conic section is defined in terms of two parameters. These two parameters here are P and E. Okay. 2P is called the latus rectum of a conic section. 2P is called the latus rectum and E is called the eccentricity. So, the orbit is defined in terms of these two things, and there is phi naught, which we have already chosen a particular value such that we shall come to that. So, phi naught has been set to 0. Okay. So, this defines a conic section. Once you tell me the value of P and E, you have told me precisely which conic section you have. Okay. And these are decided by the values of the angular momentum, the energy and the mass of the particle and the value of alpha, the reduced mass of the particle and the value of alpha. Okay, the mass m basically. Now, the first point is that whether you have, we know that there are three kinds of conic sections. There are ellipses, parabolas and hyperbolas. Okay. The whether it's a ellipse, whether it's an ellipse, a parabola or a hyperbola is decided by the value of the eccentricity E. Okay. And now let us look at this expression for the eccentricity. If the energy is if the energy is less than 0, so if the energy is less than 0, then the eccentricity is going to be less than 1, which is an ellipse. Okay. So, for eccentricities which are less than 1, we have an ellipse, and so the energy is negative. Let me connect up with what we had discussed in the last class. In the last class, we had seen that this problem is basically there is an effective potential, which is the combination of the centrifugal potential, which is positive and which dominates towards near the center, and there is the gravitational potential, which is negative and which dominates far away. Okay, so the particle here is the motion in R here is a one dimensional motion with an effective potential given by this, right. And we see that for positive energies, the particle comes from infinity and comes to a finite distance and then goes back, but for negative energies there will be bound orbits, and it will be, so if I have a negative energy like this, then the orbit is going to be restricted within these two values of R. Okay. And this is also what we see over here. If the energy is negative, the orbit is going to be an ellipse, which is a bound orbit. The value of R is going to vary between R1 and R2. Okay. So, this picture over here on the screen shows you one example of an ellipse. Okay. So, this is an example of an ellipse of one particular possible orbit. This has been drawn with p equal to 1 and the eccentricity equal to 0.3. The focus is over here, and phi is the angle. So, okay, the focus is over here and phi is the angle with respect to this direction. This, okay, what's the meaning of phi equal to 0? Let us go back to our equation now. So, phi equal to 0, if I set phi equal to 0, then p by r is 1 plus e. That is the maximum value which the term on the right hand side can have, which tells you that the value of r is minimum. Okay. So, phi equal to 0 corresponds to the nearest position of nearest approach. So, the point where it approaches nearest to the center of the motion, and okay, so that is how the origin of phi has been chosen, and this is called a the perihelion. And recollect that if I have two particles, if I start off with a two body system, then this focus is, this is one of the focus of the foci of the, one of the focuses of the ellipse. This corresponds to the center of mass of the two particles. So, one of the focus corresponds to the center of mass, and the ellipse has one of the center of mass as one of the focuses. Okay. And phi is the angle with respect to the position where the ellipse is, where the orbit is closest to the focus, to the center of mass. Now, right. Now, let us discuss a few other interesting points. Now, as you increase the eccentricity, the orbit will get more and more elongated. On the other extreme, the eccentricity equal to 0, you will have a circle, right. If you set the eccentricity to 0, you will have a circle. P by r is a constant. Okay. So, the circle, when do you have a circular orbit? we have seen that you will get a circular orbit at the minima of this potential, where there will only be one value of r. Okay. Another way of arriving at that is by determining the minimum value of the energy that you can have, right. E will be 0 and E cannot be lower than that. So, the minimum value of the energy given the value of the angular momentum, the minimum value of the energy is going to be m alpha square by 2L minus m alpha square by 2L. Okay. And this is, you can also check that this also corresponds to the minima of that effective potential. That is the minimum value that of energy that you can have, and eccentricity is 0. So, for a given angular momentum, if the particle has the minimum possible energy, you have a circular orbit. If you give it more energy, the orbit is going to get more and more elliptical. Okay. So, for the fixed angular momentum, if you increase the energy of the particle, the orbit is going to get more and more elliptical. Okay. Now, this picture, let us go back to the picture of the ellipse. So, this picture shows you the ellipse, and for this ellipse you also have the major axis. So, this is the major axis, the distance between this extremity and this extremity, and you also have the minor axis, which is the distance between the two extremities along the y axis. The latus rectum is the distance between the points where it intersects the y axis, that is going to be 2p, that you can check easily. Okay. But we are interested now in the major axis and the minor axis. Now, the major axis we know that the major axis is p by 1 minus e square. This is a straightforward calculation. You can just take the furthest distance and the nearest distance and just add them up. Okay. So, you will get the major axis, and if you write p and e in terms of the energies, angular momentum, etc., then this comes out to be alpha by 2 mod e. So, very interestingly, the major axis does not depend on the angular momentum, it is determined just by the energy. Okay. And the minor axis again, you can calculate this by extremizing y, the distance from the x equal to 0 axis, and then taking twice that, and the minor axis you can check easily, it comes out to be b minus the square root of 1 minus e square. Okay. And if you put in the values here, what you get is L divided by the square root of 2m mod e. So, the minor axis is what depends on the value of the angular momentum. Okay. So, if you fix the angular momentum, then the minor axis is fixed. Now, if you keep on giving more energy, for the least amount of energy that you can give, you will have a circular orbit with the value of the minor energy, and if you keep on giving more energy, the minor, both the minor and the major axis are going to change. Okay. So, this tells us what the orbit is going to look like in such a central force problem. Now, let us, if you want to calculate r and phi as functions of time, then one has to use this equation and obtain phi in terms of time, okay, and one has to, so it involves some integration again. Okay, we will not discuss this. So, we are interested here in r and r as a function of phi. If you want to know the exact r as a function of time and phi as a function of time, you have to use this. Okay, this will give you phi if you use this and then combine it with the things that we have worked out. The next thing that we shall work out is the orbital period of the ellipse. Of the motion. Okay. Now, we have seen that the sectorial velocity is conserved, it is related to the angular momentum and it is conserved. So, what we saw was that the angular momentum L is equal to 2 into the mass of the particle into df dt, where f is the area enclosed by the orbit. This we saw is true for any central force problem. For any central force problem, need not be gravity, any central force problem, whatever be the orbit, in this orbit, this is the center of mass, center of the force, the area subtended by the orbit at the center of the force, the rate of change of that area is constant, right. This is what we worked out. So, the sectorial velocity is constant, is conserved, it is related to the angular momentum. Okay, this is, we saw this is true for any central force problem. So, now what we can do is, we could integrate this equation over one whole orbit. So, let us say that the orbital period is time, orbital time is t, orbital period. So, we can integrate this over one whole orbit. If I integrate this over one whole orbit, then what I will get is that t, the orbital period, into L, the angular momentum, is equal to 2 m into the area. This f is the area, right. This is the rate of change of area. So, if I integrate over one whole orbit, I will get the area of the ellipse, right. I will start from here and calculate the area that it subtends at the center. If I integrate over the entire orbit, I will get the area of the ellipse. So, f is the area of the ellipse. And this, okay. So, what we have from this is that the orbital period is equal to 2 m. We know what the area of an ellipse is. It is pi into a b. So, it is 2 m pi into a into b divided by L. Okay. So, we have worked out the orbital period for this motion. It is 2 pi m a b by L, and we can substitute the values of a and b, and we can determine what this is going to be. So, let us do that. Let us substitute the values of a and b into this. So, we have seen that, so we will substitute these over here and work out what the orbital period is, right. So, let us do that. So, what we get is that the orbital period is equal to, so 2 m pi by L 2 m pi by L, and A, the major semi major axis, is alpha by 2 mod E, and B is L by the square root of 2 m mod E, and what we have is that the orbital period is equal to, so L cancels out, two cancels out, and I have pi and I have alpha. So, I have pi alpha divided by into the square root of m by 2 e cube, right, e cube m right. So, this is what we get, or the bottom line of this is that T square is proportional to the energy 1 by the energy cube. Okay, so, this tells us how the time period of the orbit, it does not depend on the angular momentum, it only depends on the energy of the particle, and it scales, T square scales as the energy of the orbit to the power of minus 3, or T scales as the energy to the power of minus 3 by 2. Okay. So, we have worked out certain features of the motion of objects under the influence of gravitation, orbits under the influence of gravitation, and the planets, the motion of our planets, of the moon around the earth, the planets around the sun, and a variety of other things. You can have binary stars, etc., etc. All of them are described to a large degree by such orbits. Now, next in this class today, let me work out a generic feature. Let me show you how we can use a generic feature to determine some properties, some very useful property of the orbit. Okay. This principle that we shall use is called similarity. Okay. So, what is this? Okay, it starts off, let us start off by noting the fact that if I have a system which has a Lagrangian L, okay, the system has a Lagrangian L, and if I multiply the Lagrangian with the constant c into L, then the equation of motion, let me remind you what the equation of motion is. Okay, the equation of motion, it is not changed. Okay. Let me write it down. This equation of motion, if I multiply the Lagrangian with a constant, the equation of motion is unchanged. Okay, just the constant just goes out. Okay, it's an obvious, it's a very trivial statement, but we shall start from this. Now, suppose my system, whatever system I have, has this interaction, the particles, the potential in this system, which could be in principle a function of R1, let us say R1 vector, R2 vector, R3 vector, etc. So, I have some potential in this, my system has got, let us say, whatever n particles, and there is some interaction between them which depends on R1, R2, R3, Rn, okay, which is there in the Lagrangian. And if I scale, suppose my potential is homogeneous in the sense that if I do a transformation, R goes to alpha R, so if my potential is homogeneous, what do we mean by that? So, if it is homogeneous of degree k alpha, so what we mean by this is that if my potential has this property that u alpha r1 alpha r2 etc. is equal to alpha to the power k u r1 r2. Okay, so, if I assume that my potential interaction is homogen, okay. Now, the Lagrangian, let me remind you, has another term which is the kinetic energy term, which is half m v square. Okay. So, if my potential term behaves like this, let us ask the question, how do we need to scale the time? So that the final thing is this original Lagrangian multiplied by just a number. Okay. So, the velocity under this transformation, the velocity will go to alpha by beta, right. Velocity will become this. Velocity is r by t, so it will become this. R has changed to alpha r, t has changed to beta t. So, the velocity will go to this, and we would like the whole Lagrangian to become the original Lagrangian multiplied by a number. So, if that is true, then the kinetic energy term, what is the kinetic energy term? Half m v square. So, we would like the v square term, the v square term will pick up alpha by beta to the power of 2. This should be the same as alpha to the power of k. Okay, this should be the same as alpha to the power of k, which implies that beta is equal to, how much is beta? Beta should be equal to alpha to the power of 1 minus k by 2. Right. So, if I scale my lengths in one way and my time in a different way, which is given over here, then I will get back the Lagrangian will just be multiplied by a number, and I will get back the same Lagrangian, I will get back the same equation of motion. Okay. So, the equation of motion is going to be unchanged. So, now let us consider a system. For that system I have some trajectory, and I scale my positions. So, I have if I scale my positions by alpha, I will get a different trajectory. I will get the same trajectory which is scaled, right. I am working in Cartesian, let us say. So, I will get a scaled trajectory which is going to be a different trajectory. Okay. So, I have some motion, I multiply that all the lengths by a number, I will get a different trajectory obviously, but then I can make it the same trajectory which I started with by just rescaling the time. That if I appropriately rescale the time, then it essentially is going to be my same old trajectory which I had started out with. Okay. So, if I scale time, so if I scale the positions, I have to also, if I so I will get a different scale trajectory. If I scale the time in a different way, okay, then I will get back the same equation of motion, same time trajectory. Okay. Now, let us see. So, let us say that there is a trajectory which has a length scale L associated with it and a time t associated with that length scale, right. A particle, let us say, covers a distance L in a time t, and now if I scale it, then how should, if I scale it so that it now covers a distance L prime, what should my t prime be? Okay. So, we can work this out. This is quite straightforward. What the condition we just went through this. So, the condition here is that L by let us see. So, L by right, L by L prime square by T prime square should be equal to L by L prime square to the power of k, right. That is the condition. This is the kinetic energy term, this is the potential energy term. Or T by T prime is equal to so, if I scale my lengths in this way from L to L prime, the time will also scale from T to T prime, which, and this is related to L by L prime in this fashion. Okay. Similarly, not only does the time change, but the energy and everything else also changes accordingly. So, we can work out how the energy changes. For example, the energy we know is L by T square, right. So, from this, or let us work out how the velocity changes first. So, the velocity v by v prime is going to be equal to, if I change my length scale, how will the velocities scale? So, I will have a new trajectory with the I will have a new trajectory, scale trajectory with the scale time. How will be the velocity, how will the velocity scale? So, you can work that out by just noting that velocity is L by T. So, this is going to be L by L prime by T by T prime, and so this is going to be equal to L by L prime to the power of, how much is it? So, T by T prime is L by L prime to the power of 1 minus k by 2. So, this is going to be to the power of k by 2, and the energy E by E prime is going to scale as L by L prime to the power of k, and one can also work out how the angular momentum L by L prime is going to change, that it is L into V basically. Now, what relevance does it have here? Now, let us apply, we can apply this to see how the time period for a gravitational. So, for let us take the gravitational interaction. For the gravitational interaction, so there are two bodies bound to each other by gravity, that is the orbit that we are considering. Okay. So, for gravity k is equal to -1. Okay. And let us ask the question, how does the time period change with the size of the orbit, okay, with the length scale of the orbit. So, that is quite straightforward. We have just worked it out, how the length scale, how the time period is expected to change with the length scale of the orbit. It is given over here, and k is -1. So, what we see is that t by t prime is equal to L by L prime to the power of 3 by 2, or the time period of the orbit is proportional to the length scale of the orbit to the power 10. Okay. So, the time period of any orbit, the square of that scales as the cube of the linear diameter, linear size of the orbit. Okay. This is referred to as Kepler's third law. And let me stop here for today. So, in a nutshell, the last two classes we have studied how the orbits in the influence of gravitational force, we have studied these orbits. Now, we shall proceed to apply this to the orbits of different planets and the moon around us and various other astronomical situations. Thank you.